Today I'm talking about the rapidity space entanglement in gauge theories. And this talk is based on this recent works. So the outline of the talk is first, maybe I give a very brief introduction to quantum entanglement, and then we will introduce high energy process in terms of large rapidity limit of quantum field theory. Then we will show our investigation of the rapidity space entanglement in subcritical systems like 1+1 dimensional gauge theories and the critical system with non-trivial evolutions. And finally, we will introduce the stream picture of the rapidity space entanglement, and then we conclude. So the quantum entanglement, I think everyone knows, is that initially that the Hilbert space of the quantum system has some sort of tensor product structure with different kind of degrees of freedoms and with a full density matrix. So the reduced density matrix is formed by tracing out some of the degrees of freedoms. Then, even this initial density matrix is a pure state, you get not necessarily a pure state. And this, from this reduced density matrix rolled out, you can define the standards entanglement entropy between the degrees of freedoms corresponding to Hilbert space H0 and degrees of freedoms corresponding to the Hilbert space H1. And roughly this kind of entanglement is it measures how, for example, a measurement in the subsystem 0 affects the measurement in subsystem 1. And it also can be used as a measure of how the state looks like. Because if the system is very large, then the quantitative behavior of this ACE is normally related to the complexity of the system, namely how many channels between the subsystem. And if we would like to write out the ground state wave function, how many terms you need in terms of the Schmidt decomposition. Therefore, this quantity entanglement entropy normally reflect deep quantitative laws in quantum many-body system, and of course, including quantum field theory. And in the literature, of course, the most well-studied example is the entanglement in the natural real space when used to define the many-body system. For example, in this one-dimensional cases, the Hilbert space consists of discretized digits along a line, and you may integrate out this part, and then you get entanglement entropy, which depends on the part of the region we would like to keep. And this quantitative behavior is well known. So, for example, for a generic state corresponding to a fermionic system, which means for at each of these digits there is a Hilbert space of dimension 2, and then after tracing out some of the after tracing out the rest, this entanglement entropy to the growth as a volume proportional to the size of the system, because this will means that in order to diagonalize the reduced density matrix, you need essentially the most component in the Hilbert space. But for the realistic system, normally observe enhanced behavior in terms of the real law, namely this entanglement entropy do not really grow polynomially in the size, but it grows at most logarithmically. And for many capital systems, observe that at long distance, this entanglement entropy is just a constant which contains some sort of UV divergence. And if you take derivative with the length to remove the divergent part, this is called this entanglement C function. It decays exponentially at large distance with this decay speed related to the mass gap of the system. And another thing you have to remember is that this entanglement entropy normally is also hard to calculate comparing to two-point functions. And here I'm not going to review this, but there are some methods to compute them. For example, in the macroscopic languages, you can use the so-called replica tricks and the conformal field theory-based method for system with conformal symmetry. And microscopically, of course, if you would like to really construct those reduced density matrix and show that the continuum limit exists, you encounter some complicated mathematical conjectures. And of course, this will also inspire some works related to so-called matrix product state entanglement renormalization group and the string duality in the these languages, which I'm not going to talk about today. So, but today I'm going to talk is a different kind of entanglement, namely for the system with a large rapidity gap, which is most suited to describe high energy experiments. For example, for the DIS at small x, the rapidity gap, it is given by the log of the 1 over x, where x is the Wilken x, or the momentum fraction of the parton. And of course, another standard example is forward scattering of two nucleons or of some two dipoles with the center of mass energy much larger than the momentum transfer. And in this case, normally the large rapidity gap is given by log of the center of mass energy. And for gauge theories in 1 plus 3 dimensions, or even in some lower dimensional models, people notice that for cross sections amplitude in these limits, there are very non-trivial symptotic behavior in the rapidity gap. And it is different from the really Euclidean short distance asymptotic behavior in a sense that even perturbatively, you do not have a full quantitative control of this, but instead people have postulated some methods to study this. For example, in one dimension in QCD, there is the perturbative evolution equations that and the related saturation conjecture. And one can also gain some insight of this behavior from string gauge duality. Therefore, but the presence of a very non-trivial symptotic behavior in rapidity gap, it means that there are non-trivial conspiracies between the fast and slow degrees of freedoms, which means the informations, they are exchanged in a very delicate and specific way. Therefore, one can actually ask a natural question, how to understand this in terms of entanglement? Does entanglement really reflect some non-trivial properties of quantum field theory in the so-called large rapidity limit or in the light front limit? And this is what the work we are doing. Well, this is what we are going to present now. So the first we present this formulation of the rapidity space entanglement in subcritical systems. So more precisely, we consider this perhaps the simplest but the physical system in the two-dimensional QCD in large NC limit, which is roughly speaking solvable. And in this case, of course, you can solve this system in the light front quantization languages and write out the so-called light front wave functions of a meson state. This meson state is very simple. It's just a two-body state with a quark and with anti-quark, and their momentum fractions are x and x bar. And you have a light front wave function phi equal phi x that satisfies the two of the equations. And in the languages, of course, of the discrete light front quantization, you need, roughly speaking, a total number of digits to really describe in the momentum fraction space to really describe a hadron with the momentum light front momentum P plus. And if you think that you put the system in a finite box in a light front X minus direction, which we call the light front space, then this N equals, roughly speaking, P plus times L minus. And this N, it also plays a natural role of rapidity cutoff in light front quantization. So then the natural formulation of the rapidity space entanglement is that here we have a line in the momentum fraction space, and the total number of digits is n, and we split the system into two segments. One is have a length x naught times n, another have a length y minus x naught times n, and this part corresponding to the so-called soft partons or small x partons, and this part represent the so-called valence partons or fast-moving partons, and then it's natural to integrate out the valence part of the parton and consider the entanglement entropy, which is a function of the x naught, the momentum fractions defining the soft or slow-moving part, and the total number of digits of n, which is in fact the natural rapidity gap. So Then in this case, since the system is only a two-body wave function, in fact, you can add to it some small number of wave functions, namely 3-body, 4-body. But as far as the number of terms are finite, this argument is similar. So now in this case, one can do a straightforward calculation of the entanglement entropy in terms of the X naught and in terms of the N. And remember, this X naught times N is equivalent to the L when you're discussing the spatial entanglement. Then we found that this Sx naught, in fact, is expressed in terms of this formula. So there is a logarithmic dependence in the size of the system, but there is no power growth. Therefore, you would say this real law is trivially satisfied for this rapidity space entanglement between different momentum fractions. And moreover, both of the Cx naught and Bx naught, this coefficient, they are purely the function of the ratios of the size of the subsystem and the size of the total system, or the momentum fraction, and they can be expressed in terms of the quark-parton distribution functions, which we call PDFs, which are important physical quantities that can be used to express a lot of factorization of the theorems in DIS and in other processes. And furthermore, the small x naught, the asymptotic behavior of this coefficient, they are expressed naturally in terms of beta coefficients that appear naturally in the Tooth equations to describe the edge behavior of Tooth equations. And these are the same asymptotic coefficient also for the forward scattering amplitude. Therefore, you can see this entanglement, of course, include some key asymptotic behaviors, the same that you observed in the forward scatterings. And furthermore, we found that it is interesting to look at the coefficient of the log term. The log term, it resembles the standard C function, entanglement C function. And furthermore, here we can show that at least for these two-body matrices, or two-body wave functions, this C function is just accumulated probabilities of finding a quark and finding an anti-quark. Namely, they are expressed in terms of the quark PDF Qx and anti-quark PDF Q bar X, and therefore it is always bounded above by a 1. And this behavior is expected to be generalized to multi-parton wave functions as well, provided that there are no additional divergences proportional to log n. So this is the result for the rapidity space entanglement described in the momentum fraction space. Of course, since we know that light from the in quantization is naturally also expressed in the light from the spatial direction, which we call x minus direction, we can actually investigate the entanglement by integrating out segments in x minus and its exterior. And in this case, it's not very interesting to investigate the ground state entanglement due to the gauge ambiguities and due to some similar issues for gauge theory. But it's more interesting to consider the so-called excited state entanglement and subtract out the ground state contribution. So now we consider a hadron state P plus described by the same Tooth wave functions in the planar limit with momentum P plus. And then this entanglement is naturally, of course, a function of lambda equals to x minus P plus, the same as the parton correlation functions or the PDFs expressed in terms of these lambdas. So now we would like to see how this relates to the PDFs, and we can derive actually a relation, namely this entanglement entropy for this hadron state between the segment with length lambda and its near and its exteriors, subtracted out a vacuum contribution, which follows a logarithmic law, equals actually to a very simple expression. First, the real law in terms of this lambda is not true. It is proportional to lambda square. And such second is suppressed by the total size of the system. the total volume, this n equals to p plus times L minus. So it's proportional to the size of the volume. The third is that there is the coefficient that is actually the second moment of the quark and anti-quark PDFs that comes here. So therefore, actually, if you investigate this light from the entanglement in the spatial, light from spatial coordinate, it can prove the second moment of quark anti-quark PDFs. And this is a nice result. So then, and we go to the more interesting situations, namely the critical system, where there are non-trivial evolutions in rapidity. So in QCD, we consider a very famous example, first investigated by Müller around 1993, which is the soft ground wave functions of a quarkonian system. Roughly speaking, you have a very heavy quark anti-quark pairs separated in the transverse direction, and they move very fast in the light-from direction and emit soft gluons. So now the point is that in the gauge theory, especially in the light from the gauge, the emission of small x gluon, they generate rapidity divergences or the small x divergences in the light from the wave functions and their norm squares. And now it is interesting to see that how to understand these divergences. And in fact, if you consider some generating functionals for those wave function squares, then you found that the leading divergences in terms of alpha s times log 1 over x, alpha s times the rapidity gap, it can actually be resummed into closed equation in the planar limit. And this can generate the BFKL equation in the linear approximation. And this also gave rises to BK-like equations for scattering for the cross sections in different approximations. So, and finally, this light from the wave functions naturally unitarize. So at least you may think that this does not generate this non-physical behaviors for S metric for the cross sections. So roughly speaking, if you consider the generating function of light from the wave function squares for pair of color anti-color sources of pair of quarks at the transverse positions B0, B1, and with some initial momentum fraction or initial upper cutoff of the rapidity gap, then then you can emit the hardest soft gluons with momentum fraction x1 at transverse places B2, and then they split the original dipole into two dipoles, and within them, these two dipoles can split it independently. So using this relations, that is true only in the planar limit, you can write out actually an equation for the generating function of the light from wave function squares, where this mu, it is accounting parameters for each of the soft gluons at the momentum fraction x at transverse position B that appears in the final state or appear in the cut. And this Z equals to a term which comes purely from virtual contributions, namely it emit the soft gluon and absorb it, and the soft gluon does not exist, does not survive in the final state. So this term, it is actually the thing we call the light from light from the soft factors. It is important quantities in the TMD factorization formalism. And of course, then the second term represents the real term, which means after emission of the first soft gluon, it's split into two dipoles with the corresponding generating functional for their light from the wave functions. And before emitting this first soft gluon, there are some virtual contributions which are resummed by the soft factors between the momentum cutoff, between the rapidity region x0 to x1. So this is some standard material in this field. Then given this light from the wave functions, for example, for one gluon state, one can try to compute perturbatively this entanglement entropy by using definitions of the rapidity space entanglement in momentum fraction space. And then you found that at order alpha s, namely the wave functions with one gluon in the final state or with no gluon in the final state, but with a one loop correction to the virtual emissions, we found that rapidity divergences leads actually to enhanced logarithmic behavior in terms of log n, where log n is the natural rapidity cutoff. There is a log square n times alpha s. And remember, in the non-critical system, subcritical system, you get only a single log to order in perturbation theory. So then we can show actually that if you go to order k in perturbation theory, it generates this behavior, alpha s to power k log k plus 1, and of course they have a second contribution, alpha s k log k, and therefore you generate large logarithms in this rapidity space entanglement. And this thing you need to resum the similar to the divergences that appears in the light-front wave functions and their squares. And fortunately, the involution equation for the reduced density matrix can still be written out in the large n limit. It can be written, roughly speaking, in this form. Namely, we consider actually a reduced density matrix with a incoming, which we trace all out, of course, all the transverse degrees of freedoms, and we left only the longitudinal freedom, degrees of freedoms in the reduced density matrix. For this, we need this reduced density matrix corresponding to initial dipole be at the transverse position, B not B1, but it has a rapidity cutoff. It has a rapidity x naught for the left-hand side of the cart or the bra, and x naught prime at the right hand of the cart corresponding to the kit. And then for the left, then since we have to trace over the transverse positions, you can still think this process as the following way, namely for the left-hand side, it meets the soft gluon at the transverse position B2, it will trace with the same hardest soft gluon emitted from this dipole, but with the momentum fraction x1 not x1 prime. This will naturally lead to another two reduced density matrix with the upper bound for the rapidity cutoff equals to x1 prime, x1 prime, but with a transfer separation from B1 to B2 and B2 P naught. And moreover, we need to add a new term in this the matrix element, namely this light front wave functions for this two soft gluons x1 prime. Therefore, this we can write a similar evolution equation for the reduced density matrix, roughly in this form. And then this, well, in principle, you should solve this to find this entanglement entropy. And we can consider some simple approximations of these equations, because these so-called BFKL kernels of this kind of form. Of course, this is only the real part of the kernel. It's quite hard to deal with. So then, following the similar spirit of Müller in 1993, we can frozen all the transverse degrees of freedoms and consider one-dimensional toy model, which means you have this form of evolution equation for the generating function. It depends only on the rapidities, but does not depend on the transverse positions. Then this equation you can solve in terms of the probability of finding n soft gluons or n-1 dipoles in the final state. They are, roughly speaking, the multiplicities that you may observe in inclusive processes. And this Pn, you found that this satisfies an exponential form of the probability distributions. And at very large rapidity gap y, roughly speaking, is log x naught times n. It has a very wide width, which grows exponentially in this rapidity gap. And therefore, you can naturally expect that this entanglement entropy, it is a log, roughly speaking, is a log of the width, but since the average value of the dipoles, or the average, the multiplicity, it also grows exponentially in rapidity gap. You found that this entanglement entropy is actually equals to A times this log x naught. Therefore, after summation, you'll find that this array law is recovered. But since there is a universal term just equals to y, which is just the rapidity cutoff, you'll find that this upper bound we obtained in the subcritical system equals to 1. It is no longer satisfied. It is enhanced. And furthermore, of course, here we notice that this entanglement entropy subtracting out a universal piece equals to log of the average number of dipoles that is probed in the inclusive process. So this example, it should be similar to the more realistic 1+3D QCD. But
there are 10 minutes remaining.
Oh, 10 minutes remain. Okay, so let me move fast. So then another interesting example is that we can study this 1+2 dimensional QCD with only a 1-dimensional transverse separations. In this case, there are still rapid divergences in the light front wave functions of the dipole, but this evolution kernel changes dramatically, which actually have only have a compact support, which means that the emitted soft gluon can only be within the original dipoles. It cannot emit outside. This leads to the so-called quenching in the phase space and leads to a much narrow distribution, which is Poissonian, with the peak not growth exponentially, but growth linearly, and with an entropy that grows much slower. And this is something we call the kinematic saturation. And then for the 1+3 dimensional system, and it is much harder to solve this evolution equation, but we can have some alternative pictures that is going to be more appropriate in the strong coupling limits, namely from the string picture. So in the string picture of high energy collisions, this parton-parton scattering, they are probed by exchange of minimal surfaces stretched in the EDS 5 dimensions. And by solving this minimal surface, you found that there is a watershed instantons, which introduces natural temperature. And therefore, there is a thermal entropy, which actually equals to the same log absolute value of n, where n is number of average dipoles. And furthermore, this entropy probed here looks like a Bekenstein-Hawking black hole because it is proportional to the averaged transverse array of the string bits of the dipoles. And finally, we can investigate this quantum entanglement entropy corresponding to the exchange of the string. And in this non-conformal situation where there is a wall and where this impact parameter is large, the string is mostly lying the wall. And in this case, we can show that this entanglement entropy growth is at the speed, roughly speaking, d perp over 6, which is so-called chaos bound. And for this, by diagonalizing this reduced density matrix, in this case, we can find the so-called cascade equations for particle multiplicities, and we can obtain actually this normalized Q moments, which can be compared to some data obtained in this LHC experiment, which looks good. Of course, this is similar, but not exactly the same as the one-dimensional reductions. But from this string picture, the qualitative features of the 1D reduction is in agreement, and they do not have actually the saturation yet, since here there is no interactions. So let's conclude. So the rapidity space entanglement can be used to probe the lifelong limit of quantum field theory. For subcritical systems, you have this form of a behavior with a bound less than 1. And for critical systems, at individual order perturbation theory, this bound is enhanced. But after resummation, you get still a recovery of array law, which only a linear growth in the rapidity gap with this S1 growth also linearly in Y. And in the 1D reductions, this S1 is equals just to A times Y, while A, you may say it is Pomeroy slope. And this is expected for 4-dimensional QCD and is consistent with the string picture. And in 1+2D, is the kinematic saturation. You have the, while you have the kinematic saturation, this entanglement, that's one grows only logarithmically in the rapidity. And finally, this eigenvalue system of the reduced density matrix, they, at least in these examples, they are identical to the particle multiplicity distributions, and in principle can be probed in experiment. And this concludes my talk.